So here we're going to implement attention, and that is this guy right here. Okay, so we're taking the query and the key and we're multiplying them together. Or actually, you shouldn't think about it as a multiplication, a matrix multiplication. Conceptually, you should think about it as a dot product between the query and the key. That dot product, we're going to scale it and mask it and then soft max it. But because we're going to be doing multiple of these dot products all in a row, we're going to combine them into one matrix multiplication. The only reason I avoid saying matrix multiplication is because usually the connotation you get with matrix multiplication is linear layers or like rotations in physics with eigenvalues. And those are great ways to conceptualize it, but that's like not the reason why we're doing it. The reason why we're doing a matrix multiplication here is because a matrix multiplication is a series of dot products. So your query and key, you dot product them together, and then you scale them. Why are we scaling it? Does anybody know?
Isn't it just to prevent them from getting too big?
Why would they get too big?
Because that's a lot of values that you're adding together.
Yes. So what Barb is saying is that if you've got 5 values, if you've got 5 values and let's say all of them have a mean of 0, or each one of them comes from a distribution with a mean of 0, then like when you dot product them together, well no, actually let's say they all have a mean of 1. When you dot product them together, on average they'll come out as 1, and so when you add all of that up, the total value will be the length of this entire thing, right? And I guess that's fine for smaller things, but what if you've got like a billion dimensions? Okay, well then you're going to have some problems. So the point is we want to scale them by the length of the, well, you want to scale them by the length of the the vector, except not exactly, because we're instead going to scale them by the square root of the length of the vector. Does anybody know why the square root instead of just the length of the vector? Okay, so the reason why we're dividing by the square root is because it's actually not so much the size that we're worried about as it is the variance. So this comment right here. The variance is the thing that's really going to be increasing. The size in my example increased because I chose a mean of 1. But in general, even if you choose a mean of 0, the variance will always be increasing. And so it's the variance that we want to scale back. And the variance is the square root of the standard deviation, is it not? I believe it is.
That is the definition of it, but why is the variance always increasing?
Why is the variance always increasing? For the exact same reason that if you have a mean of 1, the mean will be increasing. If you make your vector very long.
Okay.
Yeah. So, and that's what he's trying to say down here. Anyway, so that's the reason why we're dividing by the square root of dk. Okay, so let's do it. Okay, so the first thing we need to do is get the scores of the get the dot product, which is q times it's the query times the key transposed. And we'll call that d sub k. Oh wait, no, sorry. We're d sub k is going to be the size of the dimension. So, sorry, the dimension of the vector. So you could do query or you could do key. It doesn't really matter. You're going to say size. And now the size is going to return a tuple with the length of each dimension. And so in our case, key is going to have how many dimensions?
3?
Yes, and what will those, wait, no. They will have 2 dimensions. Wait, they might have 3 dimensions. What 3 dimensions were you thinking?
In the tips at the top, it says that there's 3 dimensions.
Really? I suppose I'm probably just not including batch.
When I printed it out, there were 4.
Really? There were 4 dimensions. Okay, well, it doesn't so much matter. Does anybody know which of the dimensions is going to be the actual, what do you call it? The actual vector that we want to do the dot product with?
It's the last 2 dimensions.
It's the last 1 dimension. The last 1 dimension will be the vector that we're doing the dot product with. If you're thinking about the entire matrix multiplication, that will be the last 2 dimensions. But it's only the last 1 dimension that we want to get the vector on. Does that make sense?
Yeah.
Why is it the last dimension? Because in the paper it said that dk is equal to d model divided by h.
It does say that, does it not? Do you know what d model is?
No.
Nor do I. I knew what it was 9 months ago, but I have since forgotten. And h is the number of heads in our multi-headed hydra. This is, but here's the thing. This is how they are deriving the size of the vector. But we don't care how they're deriving it. We just know that they already did derive the size, and now we have the size, and it is the size of that vector. We have the vector, so we can just check the size. We don't need to compute it. Does that make sense?
Yeah, that makes sense.
Okay, and yeah, the length of that vector will be the size of the last dimension in that tensor. So alternatively, you could say right here, shape at 1, size, parentheses, and dot shape do the exact same thing. Okay, so now we have the size. Now we're going to take the query and the key and multiply them together. Okay, up here at the top, there's this tip. Right here, there are 3 PyTorch implementations of matrix multiplication: BMM, torch.mm, and torch.matrixmul. You'll want to figure out which one you want to use for this lab. Okay, does anybody know what these three do?
MM takes in a two-dimensional matrix and just does an inner product on them. BMM takes a three-dimensional tensor and does a matrix multiplication on the last two dimensions. And MatMul gives you all kinds of options that you can do pretty much anything you want.
Yes, exactly. So this one with the right options can do what this one does, but this one's super simple. So we're going to do this one. Thank you, Melanie. That was very concise. I get the feeling like you've been preparing for this.
No, it makes me feel good that you mistook me for Melanie.
Oh, sorry,
she's
Barbara.
smarter than I am.
I should have known you were Barbara. Okay, so yes, that's exactly right. So the reason why we're doing BMM is because we have multiple matrices that we want to multiply together, and we want to multiply each slice of the tensor independently, and not, if you know what I mean. I'm not sure what I'm trying to say. We want to multiply each slice independently and not like across slices. Where am I? I scrolled down too far, didn't I? Here we are. Okay. So we're going to do torch dot BMM on the query matrix, and we need to transpose the key matrix. Okay, so here's the reason why I believe that the key is only 3 long and not 4 long. And the reason why is because we're going to transpose dimensions 1 and 2. So I believe the 0th dimension is the batch. The first dimension is the number of vectors, and the second dimension is the vector itself. Does that make sense? Yes, it does. Okay, so then if mask is none, is not none, then we're going to do the mask stuff. Wait, what? Oh. So I called this thing QK, but the filled in code is calling it scores. Makes no difference, so I guess I'll just call this scores as well. So all this is doing, what is this doing? That's a good question. Oh, I see what this is doing. So it's saying everywhere in the mask that it's equal to 0, set the scores equal to this, wait, is that negative to this number, which my instinct is telling me it should be that, because that's close to 0. But in the TA correct code, it also does this. So I'm not sure why. Let's see, that's just a really huge negative number. Okay, sure.
Yeah.
Oh,
the
yes.
paper said negative infinity.
Yes, okay, yeah, of course, because then when you do a softmax, that's a way to guarantee that that probability is 0. Okay, so yeah, because right here, immediately after the mask, we're doing a softmax, right? So let me draw a graph for you guys. So here's a logarithm. If you get a number that's like way the heck down here close to negative infinity, when you take the log of it, it essentially becomes 0. Or very, very close to 0. So it doesn't really so much matter what number we put in here, as long as it's just a giant negative number. Oh shoot, what happened? Does that make sense? Okay. Onward and upward. Okay, so this is essentially saying if the mask says it should be 0, make it giant negative so that when we soft max it, it is 0. Okay. Now we're going to say scores equals a soft max on those scores divided by the square root of the length of the vector. And we're going to do this along dimension -1, along the final dimension. Does this make sense? Pop quiz, why are we doing it along the final dimension?
Because that's the vector that we're actually comparing?
Yes, exactly. We're trying to softmax each vector. Question, why do we want to softmax anyway?
Get probabilities.
To get them represented as probabilities. That's perfect. And the reason why we want them represented as probabilities is because the attention mechanism is kind of trying to say, what do we think is important and what do we think is not important? What should we be paying attention to? And so conceptually you can think about that as being like a percentage of your attention. I'm putting 5% of my attention into this code and 95% of my attention into talking to you guys, and that's why I'm not very good at coding. And similarly, like, this model is going to pay attention to different words, and specifically different parts of the word, different representations of the word. And so conceptually, it makes sense for us to say, you can't be paying more than 100% attention to something. So that's why we're doing a softmax. Okay, and then the final thing is that so what we've done is we've created a vector that essentially says how much we think we should be paying attention to which parts of it, right? So we have a bunch of vectors, a bunch of numbers from 0 to 1 in our vector, and that represents whether I think I should be paying attention to this variable in the first dimension or this variable in the second one, and so on and so forth. But we haven't actually applied that attention, and so that's what the final thing we're going to do. We're going to take the vector that represents what we want to pay attention to, and we're actually going to pay attention to those things by doing the dot product with the value vector. So the overall output equals torch.bmm of the scores with the value vector. And I have no idea what this comment is for. That seems like a mistake. Any questions on that?
So why did we transpose key but not value. What was that again?
Okay, yeah, good question, good question. Okay. Woo, that is a terrible vector. My vectors always get skinny in the middle. So here we have a query vector. And here we have a key vector. Now if you talk to a mathematician, see, they always get skinny right here in the middle. If you talk to a mathematician, they will tell you that you cannot matrix multiply a query and a key together because they have the exact same size and they're not square. You need to transpose them. You can dot product them together, but you cannot matrix multiply them. You need to transpose this. So what you need to do is make this query transposed. Let me erase this. And when you transpose it, now it will become a vector like this. And the matrix multiplication of Q and KT is the exact same thing as the dot product of Q and K. The added convenience though is that when we make Q an entire matrix and K an entire matrix full of vectors, it now holds true for all of the vectors within it. Does this make sense?
Yeah, so value just happens to already be in the right shape. For when we multiply score and value.
Oh, that's a good point.
After we multiply Q and K, we have a square matrix.
Yeah.
So it will multiply easily with value.
Yeah, so these times together becomes a smaller matrix than both of them, and it's perfectly square. So then what we do is we take the square matrix and we multiply it again, not on this side, on the other side. Anyway, we multiply it not on this side but on the other side by the value vectors. Does this all make sense?
Yeah, cool. Thank you.
Okay. So that's that. And now you're already halfway done with the lab. You just got 45% of the lab. Is those 1, 2, 3, 4, those 4 lines get you 45%. Let's talk about the harder part, multi-headed attention. Okay. Okay, we've already initialized it. Hey, you know where you said what the heck is D-model? I don't know what it is either, but apparently we just pass it in here. I believe it's the dimensions of the vector representation of the words. I'm not totally sure about that, but I believe that's what it is. Anyway, so here we're going to calculate what the heck dk is, because it's going to be equal to d model integer divided by h. And that we just pulled directly from the paper. Next, dv equals dk. So the dimension of the value vector is equal to the dimension of the key vector. I don't know why they even give those different names, because it seems to me they are obviously the same. Anyway, but the paper says they're different, so we're going to make them different. Okay, now we need to make an attention head. An attention head is a linear layer. Why do we need, it's this guy right here. Now, what exactly is this linear layer doing? the wonderful thing about matrix multiplication is there's so many ways to conceptualize what a matrix is and what it is computing. And this is why I'm going to call this one a matrix, whereas before I was calling these the dot products of vectors. Because even though technically they're kind of the same thing, we're going to conceptualize this in a totally different way. And what I want you to realize is that in this entire scaled dot product attention thing, there are no learnable weights. And that should concern you, because we're doing deep learning. But there are no parameters in this entire thing. So like, what the heck, or why are we even doing this? Like, obviously it's going to have a deterministic result. And so the reason why we're doing it is because query, key, and value are actually not the same vectors. They came from the same place, but they are definitely not the same vectors. We're going to project each one of them through a matrix multiplication that is a linear layer. And I'm going to use the word projection because I don't really feel like it's not trying to bring attention to certain values. It's just... Is my internet unstable? Can you not hear me?
Joseph, you're breaking up. Going in and out.
Shoot. Okay.
That's better.
Give me 2 minutes to change to the other room. Okay. So you can think about this linear layer as projecting it into a new subspace, where each of the elements of the vector represents something completely different from what it did before. It really is a completely new vector, a completely new subspace. It just came from... It's like if we've got a ball here, and we started by looking at the ball from this perspective, and now we're going to look at the ball from this perspective. That's a terrible drawing. But you get what I'm saying. Like, in an underlying way, the ball is the same, but it's a completely different projection of the ball. And that's what this matrix multiplication is kind of doing. It's the same word vector, but you're looking at the word vector in a new way. And that's what the projection is. And the other important thing to notice is that this is where all of the learnable weights are. From here on out, it's completely deterministic till we get to this linear layer here. Does that make sense? Yay, nay? Well, I will just...
Absolutely.
Okay, cool. Okay. So, let's get back to the mouse. What's that?
So Joseph,
Yes?
the fact that the scaled dot product is completely deterministic, is that the reason that we're programming it as a function instead of as a class?
Yes. The other reason is just because it's super simple and it does not require any consistent data. Everything it does is just based on the parameters that you give it, so it doesn't need to keep track of anything. Okay. So now we need 3 linear layers. And we're going to have a linear layer for the query. And then linear, that is, I'm struggling. And each of these are going to be from the dimension of the model, which I believe, again, is the dimension of the vector embedding of the words. to the dimension of the key. And we're going to do that again for LK. I'm just going to cut that, paste that, and one more time, a linear layer for the, for the value. Okay, so there's the 3 linear layers that takes the one word vector and transforms it into the query key and value vectors, which are kind of like different perspectives on the same word object. But here's the thing, we need like 8 of these, don't we? We need, well, specifically we need H of these. And so how we're going to do this is we're going to say self dot the linear layer of Q as a list equals a bunch of clones of LQ. How many? H. That's how many. Okay, what the heck is this clones thing? Let's find it and find out. Okay, so and all clones is doing is it's making a module list of a deep copy of the module. And it's going to make n of them. Remember, a module list is super important because if it's not in a module list, if it's in a Python list, Torch will not realize that it even exists. And we're making a deep copy because we don't want them to be pointing at the same underlying parameters. They need to have unique parameters. They just need to be in the same structure. So that is why we are cloning them. Okay, back to the important stuff. Okay, so we're going to do this right here and right here. But we're going to change this to be K and this to be V, and we're going to paste that there and that there. Does this all make sense so far?
Yes.
That's lovely.
I'm going to delete that comment because I already did it. Etc. What the heck is etc.? I don't remember that part of the multi-head. Oh, it's probably this part, concatenation and linear. Huh. Okay. So let's make one last linear layer. Okay. So what is the size of the input vector that's coming out of concat and going into linear? Here's a better question. What is the size of a vector that's coming out of scaled dot product attention?
Isn't it still dk?
Perfect, you got it. Exactly. Great. So we've got a vector of size dk, and we're going to concatenate h of them together So how long is the resulting vector?
H times dk.
Yes, perfect. So we're going to go from h times dk, or it's synonymously dv. I'm going to do dv just because conceptually, the reason the dv is the dimensions of the value vector, which is the same thing as the dimensions of the key vector, but like conceptually you could make it different. We're just not going to, but for conceptual purposes, which is also why I'm going to put a dv right here. Anyway, okay, so you're going from h times dv to something of a different size. And what is that other size? What is the size of the output?
dk.
Now, why would you say dk?
Doesn't that need to be the same size as just one of the results of the attention?
Okay, so you're saying that this thing output right here has to be the same size as this thing right here?
That's my guess.
Okay, good guess, but no. If we look at the overall architecture, maybe this will give you a little hint. Let's undo that. Here we have a multi-headed attention thing, right? Right here and right here, and right here. Where does the output vector go? Generally, it just goes into another multi-headed attention, right? So in other words, it does some other stuff, some adding and norming that we'll talk about later. But ultimately, it just goes into another multi-headed attention, which means that right here, this output is going to become these inputs.
So it's D-model.
Exactly. The size is D-model. Where are we doing this? D-model. Okay. So that's the entire setup. Now we just have to actually do the forward. For every linear layer, the 3 different linear layers that we had in, oh, this is going to be a mess, in self dot this guy. Self dot that. Self dot this.
Wouldn't it be easier to use a range here?
Yeah, I suppose you could do it that way. I don't know. I view them both like kind of with the same difficulty. Anyway, the point is we're going to get each linear layer out from this entire thing. What the? That is not properly tabbed. Oh well. Then we're going to say that the result equals the attention of each of those linear layers. So len q of query len k of key and len v of value. And we're also going to pass it the mask. This all make sense? Okay.
That's cool.
So, but we're going to do this h different times, so we're going to say that this entire array of results, why is that so colon there? We're going to say that results dot append result. So now results is h long, and for each of the h, it has the attention of that layer. And then we're going to say that the overall result is going to be torch.cat each of these individual results along which dimension?
Last one?
Perfect. Why the last one?
Because we just barely created a list of them, so that's the last dimension we created.
Not quite. The reason we're doing the last dimension is because the last dimension is the dimension of the vector. And we are concatenating the vectors together. In other words, we do not want the resulting vectors to be stacked on top of each other like this, because that would make them a matrix. Instead, we want the first vector to be stacked next to the second vector so that together they are one vector, one representation of one word. Like that. That is the reason why we want to concatenate along the last dimension. Okay, clear. So there you have it. There's that. Now that we have this entire result, which is a torch tensor now what are we going to do with it?
Put it through the last linear layer.
Perfect. Put it through the last linear layer. So we're going to say out equals self dot min last of the result. And then we're going to return out. Okay, so if I'm not mistaken, we just got 90% of the lab done. But that didn't take so long. That was not so difficult.